Start with questions from homework. Anybody got any? Yeah, sure. Any homework is fine. Okay.
I'm just saying, I have to mind.
Oh, okay.
We have to do like 13 through.
I think we're up through 22 as of last classes. I think where the homework set we had ended. Okay. So today we're going to talk about 1.6 and 1.7. In section 1.6, we're going to talk about asymptotes. Hopefully you guys remember from last year, an asymptote is like a line on the graph that you can draw that the graph approaches but never crosses. So kind of visually, what that would look like is something like this. So here's a graph. And when I look at this, I see two vertical asymptotes, right? I see one here at like -3. Everybody okay with seeing that? And I see one here at +1. Right? And then I see one kind of horizontally here at +1. Everybody okay with that? Looking at the picture, identifying those? Okay. So we're stating here for a moment that technically y = 1 isn't a horizontal asymptote because we see that the graph does cross it here in the middle. We'd refer to this technically as an end behavior, since the ends of the graph still have the approach but doesn't cross behavior, even though we cross in the middle. We're not going to worry so much about that distinction inside of this section. We'll call this an asymptote for now. But last year, I think when we talked about rational functions, we made a distinction there between like the end behavior and an asymptote. So like the end behavior is the more general term, like every asymptote is an end behavior, but not every end behavior is an asymptote. Now, how do we find these algebraically? Well, the function that corresponds to the graph that I've drawn here above is this one. Oops. Hopefully you remember when we talked about rational functions last year that we can find the vertical asymptotes for any rational function by taking the denominator and setting that equal to 0 and solving. So what we have here to solve is a quadratic equation. We talked about the different ways to solve a quadratic equation last year. You could use the quadratic formula, you can factor, or you can solve directly. This one you can't actually solve it directly because you have both x's and x squareds. But we could still try to factor this, or we can always use the quadratic formula. I would try factoring since the leading coefficient is 1. It will be easy to factor if it's factorable. To factor this, I would need to find two numbers that multiply to give us -3 and add to give us +2. That would be +3 and -1. And then using the zero product property, I can set each of these equal to 0 and solve them separately. Note those are match what we observed in the graph. Everybody's okay with that? Now, if you also remember last year when we talked about rational functions, to find the horizontal asymptote is kind of an ordeal, right? There's like 3 cases, and you end up having to compare degrees of numerator and denominator, and there's a bunch of different things that can happen, and it's kind of a mess. We're not going to deal with that right now in this section. Instead, what we're going to do is we're just going to verify what we're looking at or what we're seeing in the graph numerically with our calculator. So what I'm going to do is I'm going to use my calculator, and I'm going to input progressively bigger values for x and then progressively smaller values of x, and check to make sure that we're still kind of approaching that asymptote but not crossing. So what I'm going to use are the values of 10, 100, and 1,000, and also -10, -100, -1,000. You can use those 3 values of x anytime we're doing this for horizontal asymptotes. You can use those same 3 values every time. The easiest way for me to get the values of y is I'm going to go to the y equals menu. I'm going to type in my function here. So because this is a fraction with addition and subtraction in the numerator and denominator, I'm going to have to make sure that I put parentheses around the numerator and denominator separately. So I have a parenthesis around the entire numerator, and then division, and then a parenthesis around the entire denominator. Got to make sure that parentheses around each one of them separately. Once I've done that, I'm going to change my window. All I really need to change are the x max, or the x min and the x max, and they have to match the smallest value that's in my table, so -1,000, and the biggest value in my table, +1,000. So I'll just change that. Everybody okay there? Then I'm going to hit graph. So if I look, it looks like my graph is a straight line at y equals 1, which is what we observed. That was the horizontal asymptote. To get the values for my table, what I'm going to do is I'm going to press second and the trace button and choose the value command. That allows me to pick a value for x to plug into my function. So I'll start with 10. And it gives me the y coordinate that associates with that. So this one looks like 1.085. And then I'm just going to repeat that now for 100. So here I have 1.009. And then 1,000. Here I have 1.0009. So if I look at what's happening, we're getting closer and closer to 1. We never jumped across 1 because we never got a number less than 1. So this is certainly, the left end of my graph is definitely has that asymptotic behavior that I'm looking for, right? Each one is getting a little bit smaller. We're getting smaller or getting closer and closer to 1 each time. That's all I'm really looking for. I'm going to do the same thing now with the the left end of my graph with the negatives. So second trace, we'll do -10. So that's 0.870. And then -100. That's 0.989. And then -1,000. Is 0.998. And again, I'm seeing what I would hope to see, right? We're getting closer and closer to 1, but we never cross 1 by getting bigger than 1. So that's, again, supporting what I'm seeing as a horizontal asymptote at 1. Is everybody okay with that? Now, just a calculator quirk here. Say instead I had picked value for 1,001. This is going to give me an error. The calculator is going to say invalid because if you remember, my window only went up to 1,000. The calculator, when we use this value command, can't find a point for something that it didn't graph. So if you get an error value, the problem is that your window is, you're asking for a point that you can't see on your window. So you just need to go back and change your window to make sure that the X max is big enough and that the X max is big enough and that the X min is small enough, right, to cover the numbers you're trying to plug in. But that would be the most common problem here when trying to do this on your calculator, is just forgetting to adjust your window. Is everybody okay doing this? Not much to it, right, Claire? Of course. And that's kind of it for section 1.6. Whoa. Hi.
Are you guys together?
No.
I think that helps.
Sure. You're welcome. So, function operations. This section is a little bit lengthy, but the plan is to try to get this all done today. We're going to start by defining the 4 fundamental operations: addition, subtraction, multiplication, division on a function, or on functions, I guess I should say. So we'll start with our definition. Let f and g be 2 functions with intersecting domains. We require that because we need both functions to be defined, right? If there's no x value that works for both functions, we can't really do any of these problems. So all we're doing here is just kind of saying that the problem is possible. So if we pick some x that works for both functions, then we take the sum of 2 functions evaluated at x, that's the same thing as taking f evaluated at x and g evaluated at x and adding them together. Subtraction works the same way, that f minus g evaluated at x is the same thing as f of x minus g of x. That f times g evaluated at x is the same thing as f of x times g of x. And division f divided by g evaluated at x is the same thing as f of x divided by g of x, provided that g of x is non-zero. Again, g of x needs to be non-zero because it's the divisor, right? You can't divide by 0. So this is basically what we would hope, this sort of thing works, or how we'd hope this sort of thing works. If I want to add two functions, I can just add the two functions piecewise together. It's, there's nothing fancy that we have to do. So let's run through a couple of quick examples. So let's say f of x is 2x minus 3, and g of x is the square root of x plus 2. If I do f plus g of x, according to my definition, that should just be f of x plus g of x. In this problem, f of x is 2x minus 3, and g of x is the square root of x plus 2. And then all I'd be left to do at that point is to simplify things. But there's no like terms to combine, right? I can't combine things from underneath a radical with things that are outside of a radical. And constants and variables aren't like terms to combine, so this is just really as good as we can do. Everybody's okay there? What if we did g minus f evaluated at x? Again, the definition says that should be g of x minus f of x. G of x is the square root of x plus 2, and f of x is 2x minus 3. So that's what I would write, right? Not quite. What's the problem here?
Well, hold on.
So if we look at the line above, it says g of x minus f of x, right? That negative is applied to the entire f of x. So I have to make sure that I'm distributing that negative through. So it really should be square root of x plus 2 minus 2x plus 3. And again, just like the previous problem now, there's nothing to simplify past that. Okay, so in particular with the subtraction, make sure you're being cautious about distributing a negative. Okay, easy to forget that. I would expect in a class like this, at this point in the year, more than 2/3 of us to have missed that without having this pointed out to you. Now that it's pointed out to you, I would hope that number to go down to less than half of us would make that mistake, but it would still, history tells me that that's still going to be a common mistake. That's why I'm pointing it out now and making a big deal about it. But please try to be careful about that. It's easy to forget. Please try not to forget. What if we do g times g of x? Well, again, the definition says that should just be g of x times g of x. G of x is the square root of x plus 2. Can I multiply the square root of x plus 2 times the square root of x plus 2?
Yes.
Yeah, what would I get?
X squared plus 4. Or the square root of x squared plus 4.
How about the square root of x plus 2 squared?
Oh, yeah. Okay, yeah, that makes more sense.
Right? Just if I have a times a, I'd have a squared. And what can I say about squares and square roots?
They cancel each other out.
They cancel each other out. So this really just becomes x plus 2. Does that feel okay? So again, the actual multiplication was not too bad. It was just the simplifying after that that was maybe had to remember a little bit about what was going on. Oops, I didn't want to, I was trying to color code these. So if I do a quotient, again, I apply my definition, that's going to be f of x over g of x. And in this problem, f of x is 2x minus 3, and g of x is root x plus 2. And is there any simplifying I can do here? No. So this is good enough. Everybody okay doing this kind of thing? It's mostly just practicing like simplifying an expression like we would have done last year in our Algebra 2 class, right? Not too bad. There's a fifth operation that involves functions that doesn't have a direct analog to an operation we use with real numbers, like addition, subtraction, multiplication, division. That operation is called composition. Let's define that now.
You said composition?
Yes. Yep, I'm going to get in the definition here in a minute. So we say let f and g be two functions such that the domain of f intersects the range of g. Again, all that nonsense about domains and ranges there is saying is that this is a problem that we can possibly do, that, you know, that there is an x value that makes it possible for these two functions to work, that one of them isn't always going to be undefined. That's basically all this is saying. So the composition, the way we write that, the symbol for composition is this open circle. So the way we read that set of symbols is we say f compose g of x. That's not the letter O. This is not the word fog. Please don't call it fog. It hurts my ears, makes me want to stab myself in the ear. Makes me very sad. Okay? There's no fog. It's not a thing. Okay? And the way we do composition, so f compose g, what it's saying is we're just going to plug the function g into x. Or into f of x, I should say. So let's look at an example. Or a couple of examples. So let's say that f is 2x squared minus 3x, and g is negative 3x plus 4. So let's say we want to do g compose f of x. Well, by our definition, that should be g of f of x. In this problem, I know that f of x is 2x squared minus 3x. And when I have function notation like that, this is telling me that I'm going to plug 2x squared minus 3x into the x's in g. So I'm going to write this as negative 3 times 2x squared minus 3x, and then plus 4. Joe?
So the highlighted portion, is that basically representing the x?
That's what we're plugging in and replacing the x. Yep,
Okay.
exactly right.
Okay.
Yep. So that's right. That's what we got. So at this point, the composition is done, but there's still some simplifying to do. What would I need to do to simplify this expression? Distribute that negative 3 through. So when I do that, I have negative 6x squared plus 9x plus 4. None of those are like terms, so this is as far as we can go.
Saw those last two.
We did.
So should we should just leave it like that? We don't need to go like all the way through.
Well, this is not a solving problem. It doesn't say solve for x or something,
true. Yeah,
right?
Yeah.
So
Yeah, that's right.
the directions we're just trying to do the operation.
Okay.
So when we get to it fully simplified, we're done.
Okay.
Don't have to factor, you don't have to solve anything.
Yeah.
It's just just following the directions.
Sounds good.
Okay, if we wanted to do f compose g of x, again, our definition says this would be f of g of x. In this particular problem, g of x is negative 3x plus 4. So f of negative 3x plus 4 says I'm going to plug negative 3x plus 4 into the x's in f of x. So I'd write 2, and then in place of the x, I'm going to write 3x plus 4, and then squared, minus 3, and then in place of the x, I'm going to write negative 3x plus 4. Now the composition is done, but what I have left to do is still some simplifying. So there's several things that I would need to do here. According to the order of operations, the first thing I should do in this is,
Parentheses.
well, if I look inside the parentheses,
Yeah.
there's nothing to do inside the
So
parentheses.
the exponent.
So the exponent would be next. How do I do negative 3x plus 4 squared?
Do you attribute the 2 to both numbers?
Definitely not.
No.
What does something squared mean? If I have 2 squared, what do I get? 4. How did you get 4? 2 times 2, right? So negative 3x plus 4 squared is negative 3x plus 4 times negative 3x plus 4, right? If I write it that way, what would we need to do? FOIL, right? Now, my suggestion would be to leave the 2 for last. I would FOIL that stuff and then distribute the 2 through. I think is the easier way of going about doing this. Everybody okay with that? And now we'd really combine our like terms there, and instead of writing that negative 12x twice, I'll write that as negative 24. And now we would want to do our distributing, right? So I have 18x squared minus 48x plus 32 plus 9 minus 12, or 9x minus 12. And the last step then would be to combine my like terms. So negative 48x and positive 9x give me negative 39x. Positive 32 and negative 12 give me positive 20. And that's as good as we can do. We okay with that? So these were both composition problems. The composition part was really the same amount of difficulty for each of them. What became more difficult was the simplifying, right? This second example had a heck of a lot more simplifying to get to a final answer than the previous one did. And that's just how it goes sometimes. There's a big takeaway, though, from these two examples. If you notice, though, these two answers, not the same, clearly, right? What this tells me then is that composition doesn't work the same forward and backwards. Right? Addition does. 1 plus 2 is the same as 2 plus 1. Right? Doesn't matter the order that you add two things. Composition, though, F compose G and G compose F, we just saw that we get two decidedly very different answers here. Everybody's okay with that? Now, there is special cases where they do give you the same thing. One of those special cases we're going to define right now. So we say that if f and g are functions, we say that g is the inverse function of f, if and only if. When we do the composition both ways, they both give us x as the result. Everything cancels out, and all that we're left with is x. In this case, we would write g of x as f inverse of x. So that negative 1 exponent, when it's attached to a function, doesn't mean to make the reciprocal like it would for a number or a variable. It's just part of the name for this particular kind of function, where when we compose it with f, all we get is x. So the idea here is, okay, I'm going to take some input x, and I do g to it. That gives me some output, g of x. If I then take that output and plug it into f, I'll then get x back, the original number that I started with. So the idea here is f is basically going to undo everything that g did to x. And the reverse would be true, that g would undo everything that f does to x. That's what we mean by an inverse. So it's just the function that kind of undoes whatever the other function was doing. So let's look at some examples of finding inverses. So let's say we have our function written as this mapping diagram. I'll call that function f. So in f, 1 goes to 4, 2 goes to 6, and 3 goes to 5. In my inverse, I have to reverse the direction. So I have to take 4 and send it back to 1. I'd have to take 5 and send it back to 3. And then I'd have to take 6 and send it back to 2. And this is what we'd call f inverse. Jack? Sure. Is everybody okay with that idea? You're basically just reversing the direction of everything, right? Simple enough idea. If we look at this example, notice that f inverse is also a function, right? Everything in the domain is used. 1 or 4, 5, 6 are all used, and they all only go to one place, right? 4 goes just to 1, 5 goes just to 3, 6 goes just to 2. So this is definitely a function. Maybe we should be... let's look at a different one. Let's say that our function is written as a set of ordered pairs. So when I write my inverse, what's that going to look like? Well, in f, we're sending -2 to 4. So our inverse has to send 4 back to -2. In the function, we send -1 to 6. So in the inverse, we have to send 6 back to -1. We send 3 to 8. So we're going to have to send 8 back to 3. And then we send 5 to 8, so we have to send 8 back to 5. Everybody okay there? Is this a function?
Yes.
No. Why is this not a function? Ellie? Yeah, so I have the x value of 8 that goes to 2 different places. 8 goes to 3 and it goes to 5. Very good. So we've seen now from example that this inverse isn't always going to be a function. One of the things that we'll do here in a few minutes is figure out a way to predict when our inverse will give us, or when our inverse will be a function, based only on f, right? We'd prefer not to have to find f inverse to decide if it's going to be a function or not. We prefer to be able to do that before we even have to find the inverse. And that is possible. We can do that. Another way to represent a function is with a graph. So let's say that we have this graph. What I would do to find the inverse for this, what I think the easiest way to do this is, we're going to just pick a couple of points off of our graph. So maybe that's the point negative 2, 0. Maybe that's the point 0, negative 3. And maybe that's the point 4, 4. What I'm going to do next is I'm basically going to do the same thing as I did before. I'm going to transpose the x and y coordinates and replot those and then kind of connect things. So negative 2, 0 goes to 0, negative 2. Zero, negative 3 becomes negative 3, 0. And 4, 4, well, that still stays 4, 4. Everybody's okay there? Now keep in mind that 0, negative 3 was the vertex for my original. So negative 3, 0 should be my vertex for my inverse. So when I draw this, it's going to look like, something like this. Everybody okay with that? So it just kind of looks like I've taken the thing and rotated it a little bit. Really, it's not a rotation, though. What we're actually doing is if we have this line y equals x, really what I'm doing is I'm reflecting f across that line to get f inverse. So like when I reflect this part of f across that green line, I get that part of the inverse. When I reflect this part of f across that green line, I get this part of the inverse. And when I reflect this part of f across the green line, I get this part of the inverse. Now that's a lot harder to see visually, like to do that. That's why I like to assign the points and do the point transpose and then draw the picture. But as a nice little check, you can just like kind of draw that line y equals x in and just visually check to see that, okay, looks like I drew that right because it seems to all match up. Is that okay? Again, a little trickier to see that in your mind's eye. Hopefully by like color coding it a little bit, it's a little bit easier to see kind of how the parts match up or whatever. Okay. So again, if we look at this one, f inverse, is that a function? That sideways parabola, is that a function?
No.
No, right? Why not? Fails the vertical line test. Very good. So we've seen a couple of examples now of things that are inverses, and sometimes they've been functions and sometimes they haven't. Let's kind of build out how we can predict what's going to happen. So I'm going to define some vocabulary that we're going to use to describe that when that's going to happen and when it won't. So we're going to describe three terms. The first term is called onto. We say that a function is onto if every element in the range is mapped to by some element in the domain. And we'll do some examples here in a second to kind of illustrate to you what it looks like for something to be onto or not. But I want to do all the vocabulary because I'm going to do multiple things for one example. We say a function is considered one-to-one if every element in the domain maps uniquely to a distinct element in the range. And lastly, we say that a function is considered bijective if it's one-to-one and onto. So 3 definitions, right? Now, let's describe like what this is going to actually look like when you look at a mapping diagram or a function or a graph or whatever, right? So let's say we have this mapping diagram. Say 1 goes to 4, 2 goes to 5, and 3 goes to 5. So if I look at this function is not onto because I have something in my range that isn't paired to. Is that okay? Relatively easy. It's also not one-to-one because I have something in my range that 2x is paired to. Everybody's okay here? Let's look at what would happen now if I found the inverse for this function. So the domain would be 4, 5, 6, and the range would be 1, 2, 3. So 5 goes to 2 and 3, and 4 goes to 1. So this thing is clearly not a function. But it's not a function for 2 different reasons. One reason it's not a function is because we have things in our domain that aren't paired. Yes?
Or can I just do the rest of the definition just a little bit?
Sure. Right? One reason it's not a function is because I have a domain that's not paired. Another reason it's not a function is because I have a domain that goes to 2 separate ranges. Right? That's another reason it's not a function. So I can see if my function is not onto, its inverse can't be a function because I'll have a domain that's not paired, right? Okay. And if my function was not one-to-one, its inverse can't be a function, because that means it'll have an x that's paired to two different y's. So what does this lead me to say then? If f of x is one-to-one and onto, then f inverse of x is a function. So my check to tell if f inverse of x will be a function or not is I can just check f to see if it's one-to-one and onto. Joe?
So if it is one-to-one and it is onto, that's when we can say it's bijective?
Yes.
Okay, so in this case, it would not be bijective, right?
Correct. So let's look at some more examples, right?
Yeah.
So this is my big conclusion, though, that I'm reaching. But let's look at some more examples. Let's look at some graphs this time. So let's say I just have a parabola. Is this graph going to be onto? Are there y coordinates that are not used by this function? Well, sure, right? There's a whole bunch of y coordinates down here that don't have a point associated with that y coordinate. Does that feel okay? So this is not onto. Is this one-to-one? Are there any points that use the same y coordinate? Well, sure, right? These things that are on the same horizontal line use the same y coordinate. So they're not one-to-one. So we can use this horizontal line test to check if a function is one-to-one. That's an easy check for a graph. So you might be thinking, okay, all right, so you've given me two examples that are not one-to-one and onto. Give me something that is, right? Let's look at something that is one-to-one and onto. Well, how about just like a linear function, like a line? That's onto, right? All the y coordinates are covered. And it's one-to-one. Those y coordinates are used only one time because it would pass a horizontal line test. So that's an example of something that's bijective. It's one-to-one and onto. Well, how about what if I want something that's just one-to-one and not onto? How about this? That's one-to-one, right? There's no y coordinates that are used more than once, but it's not onto because there's lots of y coordinates that aren't used at all. Okay, well, how about something that's onto but not one-to-one? Okay. How about something like this? That's onto, right? All the y coordinates get used. I have an arrow pointing up and down. But it's definitely not one-to-one because it would fail a horizontal line test. Does that feel okay for everybody? Give us a picture about what this one-to-one and onto-ness is all about. And the graphs are the examples that I would expect for you guys to deal with. You know, if I give you the picture, you could say whether it was one-to-one or onto. Beyond that, I think is beyond the scope of this course. Or a mapping diagram. Again, I think that's realistic. Joe?
So does the horizontal line test basically tell us if it's going to be one-to-one?
Yes.
So if, like, for example, the one that is one-to-one, since only one y intercept is being used, that's why it's, what's the word, 1-to-1?
Yes,
Since there's like multiple as 3, I guess, on the next one, that's why it's not?
yes.
Okay.
Works the same way as the vertical line
Okay,
test would.
yeah, yeah.
Yep, it just go in the opposite direction because we're checking for repeated y's instead of repeated x's.
Okay.
Okay. The last thing we need to do, or last thing we still haven't talked about yet, is we've talked about finding inverses for mapping diagrams for sets of ordered pairs, and for graphs. We haven't yet talked about finding an inverse for an equation. So let's do some examples of that. So let's say we have this function, and we want to find the inverse for it. So what I'm going to do, or the process I'm going to use, is I'm going to rewrite this as a y equals. So I'm going to take it out of function notation. And then I'm going to get the x by itself, just using algebra. So in this case, I'm going to add 7 to both sides. And then divide both sides by 3. So the x is all by itself now, right? Then I'm going to swap the names for the x and y coordinates. So everywhere where there's an y, I'll write an x. And everywhere there's an x, I'll write a y. But everything else stays the same. I just changed the names for the variables. All my x's I turned into y's, and all my y's I turned into x's. And then I'm going to put that back into function notation. And call it my inverse. That's it. Now, I can say that these two things are inverse. If I want to confirm that or to prove that they're inverses, I need to use my definition of inverse that we defined just a few minutes ago. So what I would need to do is I need to show that f compose f inverse of x is equal to x. And I'd also need to show f inverse of f, or compose f of x is equal to x also. So let's do that, just to kind of confirm that this is my correct answer. So my definition of composition says f compose f inverse of x is equal to f of f inverse of x. The f inverse that I found was x plus 7 all over 3. And then I'm going to plug that into f. So I'm going to take this and plug it into the x in my function. So I have 3 times x plus 7 over 3 minus 7. So if I look here in the parentheses, I have a times 3 and divides by 3. Those cancel out. And I have a plus 7 and a minus 7. Those cancel out. And I'm left with x, which is, according to my definition, what I wanted to get. I'm not done. I still have to do the other direction, but it's going to work pretty similarly. So f inverse compose f of x is f inverse of f of x. In this problem, my f of x was 3x minus 7. When I plug that into my f inverse, I have 3x minus, I was using green. I have 3x minus 7 plus 7 over 3. Well, minus 7 and plus 7 add to give me 0. And then 3x divided by 3, the times 3 and divides by 3 cancel. And I'm again left with x, which is what I was supposed to get, if this is correct. So what I've done is I've just checked and found that, yes, these two things are inverses. I did the procedure to find them, or find the inverse, and then I confirmed it by doing that process. Is everybody okay with that? Jay? Absolutely. Let's do some more examples, okay? In particular, the finding the inverse process. So let's say that we have something that's a little bit more complicated. So let's say our function is 2x plus 5 over 5x minus 8. My procedure in general is going to be the same. The details will be a little bit different though. I'm going to start by getting rid of the function notation. And then I'm going to want to get the x by itself. The problem here, though, that makes this much more difficult than the previous one is I have x's in 2 locations instead of 1. Everybody, you see that? So the first thing that I would do here is cross multiply to get rid of the fraction. Because fractions, yuck. But that's pretty nice, right? No more fraction now. I'll just distribute the y through. Whoop, whoop. And now I'm going to move the stuff with the x's onto one side and the stuff without the x's onto the other. So I'll subtract 5xy to both sides and then subtract 5 from both sides. If you look on the left-hand side, I notice that both terms have an x in them. So I can factor off that greatest common factor of x. Notice in doing that factoring, my x's have gone from being in 2 locations to being in 1 location. Yay! And so then next I'll divide both sides by that 2 minus 5y. And now I have my x by itself. I can then swap my x's and y's. And write this in function notation. Probably along the way, if it were me, I would also do something about the negative sign situation in this. So I would probably like multiply the top and bottom by -1 just to get this a little bit nicer. You didn't need to do that. I'm just saying that I would, because like, who wants to deal with 3 negative signs when you could deal with 1? You know? Okay. Let's do another. FGH, I think, right? All right. First step, what do I do? just rewrite it with a y, right? Okay. Now we're trying to get the x by itself. What would I do first to do that?
You're gonna take the 4 and put it on the y side.
Okay, add 4 to both sides. Good. Then what?
We would divide by, is it 5 plus 4?
We'll divide by 3.
Oh, yeah, to get the x by itself. Yeah.
Yep.
And
And then we would do square root both sides. Now remember, very important, when we square root both sides of an equation, what happens? You get a plus or minus. That again is something I would expect without being reminded that probably 2/3 or more of us would have forgotten. Oof, so many things to remember. And now the x is by itself, so I can swap the x's and y's and rewrite this as, or in function notation. I'm going to do that all in one step if everybody's okay with that, rather than separating it out.
that's our final answer.
That's your final answer.
So basically, once you get to the, once you bring the, or like get the x alone,
Yeah.
clear both sides.
You're basically done, right?
Yes,
You just rewrite your answer.
Right, you just flip the y's and the x's, and then you put the h minus 1. or
Yeah, you
whatever
put the
variable
function
is.
notation back
Yeah,
in.
yeah, yeah.
Yeah.
It's not bad.
No, the hardest part is getting the x by itself, right? It's doing that algebra. Let's see, I think is the next letter in the alphabet. What if we have square root of 12x plus 5?
So y equals,
Yep. So we just change it to y equals to start. And what are we going to do first here? Getting the x by itself.
can we subtract 5, or are we not allowed to do that?
Oh, we got to get rid of the square root before we can get at the stuff underneath it.
So the square.
So square both sides to get rid of the square root. Yep. And then we can subtract the 5. And after that, we should
Square root again, to get rid of the square.
divide by 12, right? We got to get the x by itself. And now we're basically done, right? We'll rewrite in function notation and swap out the x's and y's.
So we can keep the x squared, the final answer?
Oh, yeah.
Not a problem?
Nope,
Okay.
no biggie.
Okay.
No biggie. Feel okay there, my peeps? See, J is next. Now we're getting into the tricky stuff here. See who really remembers last year. Well, we start by,
Y equals.
yeah. So notice that this is a exponential equation, right? Because the x is in the exponent. The first thing we should do, though, is
Forgot.
I would get rid of the negative 1/2. How would I do that?
The reciprocal.
I would multiply by the reciprocal. You don't want to distribute because there's not really anything to distribute to. You can't multiply the negative 1/2 and the 3 because the exponent attached to the 3. So multiplying both sides by -2 gives me this. Yes, sir. Of course. Everybody's okay to hear? How are we going to get rid of that 3? What cancels out an exponent base? Does anybody remember? We did this last year.
Isn't it like, it's not long.
It is a logarithm. Yes, good.
Log of both sides?
Which logarithm? Log base 3. Very good. Yes, so we'll do log base 3 to both sides. Because we remember that a logarithm cancels an exponent base. So log base 3 cancels the exponent base 3. Does that ring some bells? Should at least look familiar. This is the point of doing all these examples here, is it just allows me to review all these different function types from last year. And then the last step would be,
Switch the variables.
we gotta get the x by itself.
Oh, divide by 4.
Divide by 4. I would write it as 1/4 times the logarithm. I think that just makes everything a little bit more clear. Because at one point it could be difficult, like you could be convinced of where to put the divide by 4. Is it over everything? Is it over the stuff inside the parentheses? Someplace else, you know. If you do it that way, though, it's completely unambiguous. And now we switch the variables and rewrite it in function notation. 1/4 log 3 negative 2x. And one more. I think K is the letter I'm at now. What did I write? I picked that. That's it. Okay. Okay. So I have 5/3 ln of x, or 7x minus 1. What did ln stand for again? Natural log. That's good. Okay, but before we get into any of that, what do we start by doing? Y equals. Okay. And then what should I do next to start getting the x by itself?
Multiply 3 plus the reciprocal.
Good. Multiply both sides by the reciprocal. Very good. Then what do I need to do? Yeah, so I need to use an exponent base to cancel out my logarithm. So which exponent base is going to cancel out the natural log? Not 10. It's the other one. E.
Oh yeah, we did that.
Natural log is log base E. Just log is log base 10. Those were the two special ones. So the common log is log base 10. That's just log with no subscript. So I'm going to write my exponent base of e to both sides. That's why the e is enormous. Is the left-hand side of the equation is in the exponent, and then the right-hand side of the equation is in the other exponent. Exponent base e will cancel log base e. Now continuing to get the 7 or get the x by itself.
Add 1 to both sides.
Add 1 to both sides and then
Divide by 7.
divide by 7. I'm going to do that all in one step.
Flip our sign every time.
Yep. So k inverse of x is equal to e to the 3/5 x plus 1 all over 7. Pretty rad, my dudes. Let's stop here because, I'm pooped. I don't know about you guys. Here's the bad news, though. Section 7 was the biggest homework section.
Oh.
So we're up to 56.
These problems take a long time.
Some of them have a lot of parts to them.
Is this due Sunday?
So let me look here on how I did this.
Because I think we have 19.
Yeah. Hold on one second. Let me go look at how I broke this up. Because I think I did break this.
Okay, that's fine. Whatever you guys do.
Let's see. Okay. So FYI here, guys. Sunday's homework check is 13 to 24. Okay. So Sunday's homework check is 13 to 24. The next homework check after that will be 25 to 56, plus the chapter review, because this is the last section we're doing in this chapter. So for Sunday, you really don't need to have that much done, but goodness, don't put off all that stuff till next week, especially because you'll be taking the test next week and you'll want to do some of these problems before then. So the plan is next class, for us that's Tuesday, we'll work on the review. And then the following class, Thursday, would be the test. So like a week from today. Today's Thursday, right? Yeah, so it'd be a week from today.
Tomorrow.
A week from tomorrow. Excuse me.